Good morning, I am Mr. Ish. Thank you for joining me. In this video, we're talking about the Nernst equation, and you could write that out as this, the Nernst equation. It's an excellent equation because it relates the potential at an electrode with regards to the concentration of the solution of that electrode. What does all of that mean, and what are we looking at? Well, we have the Nernst equation here. You can see E. And this can be the potential of an electrode is equal to the half cell potential minus RT over NF, the rate constant times the temperature divided by moles and the Faraday's constant multiplied by the natural log and the quotient of your equilibrium expression. Now look at that equation right there. This part right over here from here to here can be rewritten as that. RT over NF, natural log of that, is equal to 0.05916 over N log of that quotient. N over here refers to number of moles. R equals 8.314. F is equal to 9.649 times 10 to the 4, and temperature at 25 degrees or 298 Kelvin. You have to pay special attention over here. RT over NF, natural log of this quotient, which I'm calling X, is equal to 0.05916 over N log of that quotient X. You see the natural log and the log. What is that telling you? Paying special attention right here to the natural log and the log conversions, you're learning this. The natural log of an item is the same thing as natural log 10 multiplied by log of that item. And you're seeing this. This right here is the same thing as this, but you have to multiply it by coefficient of natural log 10. Take any number, take its natural log, a positive number. It'll be the same thing as a log of that same positive number multiplied by natural log 10, and that's how this conversion comes into play. This form of the equation is easier than that. Look right here, if I'm doing like 40 and I take its natural log, it's 3.688, I'll save that. I can do 40 and I can do a log of it and multiply it by 10 natural log, and it'll be exactly the same. It zeroes out because I took the difference of the two. Since they're the same, they zeroed out. The log of a number multiplied by natural log 10 is the same thing as the natural log of that number. Now let's get back to the topic. You want to apply the Nernst equation individually to each electrode. Your format for doing these type of questions is going to be your cell, the potential of your cell is equal to your E positive minus E negative. What is this telling you? The positive electrode minus the potential at the negative electrode. What's your positive electrode? It's your cathode. What's your negative electrode? It's your anode. Why is that the case? Because in an electrochemical cell, at the anode you're having oxidation. What is oxidation doing? Take the anode and look at it in terms of the oxidation occurring. You're generating electrons. Those electrons are going to go into your anode and then go into your circuit. At the cathode, you're collecting your electrons, but they're going to attach to a certain metal and they'll convert it into a solid. The negative electrode will be your anode, the positive electrode will be your cathode. You got to remember that because the format you're using is this. What are the parameters of this question? Your anode is cadmium, your cathode is silver. You have 5 micromolars of silver nitrate in your cathode solution. You have 1 molars of cadmium nitrate in your anode solution. We have to find the potential of this entire cell. I'll show you how you go about doing it. Remember, your positive electrode is your cathode, your negative electrode is your anode. You keep that in mind. You'll individually do the Nernst equation for each electrode, and you'll always look at your half reactions in terms of reduction. Your silver is going to represent your cathode because based on an activity series, cadmium is more easily oxidized and silver is more easily reduced. Hence, silver will have a preference to be reduced. It's going to take the cathode position, which is right here. It'll be positive. What will be the half reaction here? It'll be always written in the form of a reduction, and you'll have that. Now you need to have the value of this from your activity series, and you can easily obtain that. The value over here is 0.799 volts. You're going to send everything right here through the Nernst equation. Before we get to that, now think about your oxidation reaction, and that's going to be indicated as negative because the electrode where you're doing this is the anode. Here you're going to be looking at your cadmium, but again you're going to write everything with regards to this entire procedure in terms of reduction. It'll be cadmium 2 plus 2 electrons to give you cadmium. This prefers to be oxidized, but you write it as reduction reaction because of the Nernst equation. You look at everything in terms of reduction. you have to look at the value of this based on your activity series. The value of this is minus 0.402 volts. If your activity series was in an opposite format where your reaction is this, where your activity series table is giving you the oxidation reactions, you'll have a 0.402 volts. But since you have to present everything here in reduction, you'll flip this around, you'll change the sign, you'll get your minus 0.402. So it wouldn't really matter. You'd still have everything right. So you have to balance it. When you're balancing this, all you're seeing is you have to multiply this by 2. You'll have 2 all the way across. This already will be balanced because this will dictate the coefficients of silver. Now you would have to look at everything with regards to the Nernst equation individually for each of these metals. This right here is going to be your E positive because it's the cathode. It'll be that. This right here will be your E negative because it'll be the anode, and it'll be represented by that. Let's look at the Nernst equation for this and apply it. Here, your E positive value is going to be your potential of this reaction, 0.799. The coefficient never multiplies with this. The coefficient only affects your equilibrium expression, reactants and exponents and things like that. It never multiplies with your potential of that half reaction. Minus 0.05916 over N. N is the number of moles which are involved. Well, you'll have 2 moles because the coefficient 2 is coming into play, and then you'll have now log. The product over here in all instances is these metals which are solids, and you know solids are kept out of reactions. You put them as a 1 divided by the silver. But silver concentration here is 5 micromolars. It's 5 times 10 to the minus 6. Remember, micro means 10 to the power minus 6, and then square. Why am I putting a square over here? Because when you put the coefficient over here, you're looking at 2, 2, 2. And that coefficient comes as an exponent. You have to do this entire computation and you'll have this value, and let's do it. We'll work from this side towards that. I have 5 exponent 6 minus, I'm going to square it. I'll take the reciprocal of it because it's 1 divided by. Now I'll do the log of it. Now I'll multiply by 0.05916 divided by 2, but theirs is a negative. I'll put a minus before it and I'll add it to this. Plus 0.799, and I'm getting 0.48539. Let's put it here, 0.48539 volts. Now let's look at everything with regards to the anode. Here you're looking at this minus 0.402 minus 0.05916 over 2 log this right here. We'll have a 1 divided by cadmium concentration, which is about 1 molar. Log of 1 is always a 0. All of this right here will zero out. All of this right here will zero out. You'll see it. 1 log is a 0. It zeroes everything out. The only thing which remains is this minus 0.402 volts. Minus 0.402 volts. Here's your 1. Potential of the electrode for the anode. Here's your potential for the electrode, which is the cathode. Your potential for the entire cell is equal to the cathode minus the anode, which is 0.48539 minus the potential for the anode, which is a minus 0.402. You essentially adding them up. You have here a 0.88739 volts. It's a positive. What does a positive mean? It tells you that this entire electrochemical cell, where you're using a chemical reaction to generate electricity, is going to be spontaneous. These values being positive are spontaneous. If it was a negative value, it would not be a spontaneous reaction. You would have to make it spontaneous by means of inputting electrical energy, but that would defeat the purpose of a galvanic cell, where you are looking for a spontaneous reaction to generate electricity for you. When you're looking at the Nernst equation, keep in mind again, this entire expression here can be equivalent to that. The natural log gets converted to the log. This RT or NF becomes 0.05916 by means of that natural log 10 coming into play. And let me show you that. RT or NF, 8.314 times temperature in Kelvin 298 divided by your Faraday's constant 9.649 exponent 4. The n stays as the n in the denominator, but you multiply this by natural log 10 and you'll have 0.0591. The decimal places are creating the difference here, but it's 0.0591. So keep that in mind. What I showed you at the very beginning, the only difference between this and this is the natural log of a value is equal to the natural log 10 multiplied by the log of that same value. Hence, you're getting this conversion. Everything with regards to Nernst equation you're writing here with regards to half reactions in a reduction form. E cell is equal to the potential at your cathode minus potential at your anode. This can also be looked as your right electrode and your left electrode. By convention, the right electrode is your cathode, your left electrode is your anode. Your anode is negative because it's collecting the electrons to send through the circuit. Your cathode is a positive electrode because it's going to use up those electrons for a reduction reaction. That's all you want to keep here in mind. At the very end, you're looking at the sign. The sign of a cell being positive is a spontaneous. If it were negative, it's not spontaneous. The concentrations play very well into this by means of this quotient here of the products to the reactants. You can see that has all come into play. So this right here was a video on how you utilize the Nernst equation individually for each electrode. Then the outcome of those electrodes with regards to potentials feeds into your overall potential for your cell. Thank you for watching. Have a good day.